Okay, 7-8 says inverse functions and relations. So an inverse, remember a relation is just a set of ordered pairs. So an inverse relation is a set of ordered pairs obtained by switching the coordinates of each original ordered pair. So if he was an X, he's now a Y. If he's a Y, he's now an X. We just flip-flop him. So, number 1 there says the ordered pairs of the relation 1, 3, 5, 3, 5, 0, 1, 0 are the coordinates of the vertices of a rectangle. Find the inverse of this relation and determine whether the resulting ordered pairs are also the coordinates of a rectangle. Okay, so here's my inverse. I'm just going to switch him. If he was an X, he's a Y. If he's a Y, he's now an X. So 1, 3 becomes 3, 1. 5, 3 becomes 3, 5. 5, 0 becomes 0, 5. And 1, 0 becomes 0, 1. Okay, let's graph it. 1, 2, 3, 1. 1, 2, 3, 1, 2, 3, 4, 5. 0, 5, 0, 1. What do you think? Did we get a rectangle? Yep. So not too bad, right? We just switched the ordered pairs. So then it says an inverse function, and it says if f and f to the minus 1. This is just function notation that means inverse. Okay, so we just put f to a negative 1 exponent. If they are inverse functions, then f of a equals b if and only if the inverse function of b equals a. Well, that's the same thing. Think about a and b as ordered pairs, right? This would be x and y, then this would be x and y. So we're going to do the same thing. Okay? So number 2 there says find the inverse of f of x equals negative 1 half x plus 1. Then graph the function and its inverse. Okay, well remember this is a fancy way of writing y. So this guy is really y equals negative 1 half x plus 1. Well, what did we do at the top to get the inverse? Switch the x and the y, right? Guess what? We're going to do the same thing. But now we have a letter. So this guy is now x equals negative 1 half y plus 1. So I just switched the variables. All right, now when I graph things, what form do I like them in? Especially lines. Y equals, right? Or like slope-intercept form. This guy would be a whole lot easier to graph if the y was by himself. So let's rearrange that bad boy. What should I do first to get the y by itself? Subtract 1. Then what? Multiply by negative 2? Is that what you said? Yep, sure did, right? So I get negative 2x plus 2 equals y. And then just for sake of correct mathematical notation, I'm going to replace the y with the inverse. So the inverse function of f of x is negative x plus 2. That makes sense? So I just replaced the y. Remember, f of x is fancy y. So I went back fancy. Now it says then graph the function in its inverse. Okay, well the function they gave me at the beginning was negative 1/2 x plus 1. Okay, so that guy's in slope-intercept, so I'm going to start at positive 1. And my slope is negative 1/2. Down 1, right 2. If you go to the right, you're always right. Okay, so there's my function value, my function equation, my function line. And now I'm going to start at positive 2, and I'm going to go down to right 1. Wow. Kevin was a little excited. Now, essentially, what we're doing is we're reflecting that guy across the line y equals x. Let me find, I need a different color. Here we go. Nope, that's blue. That's not work. Let's try pink. Here we go. We, at this point right here, when we switch the x and the y, we said y equals x and x equals y, right? When we switch them. So the line y equals x, think about the line as 1x plus 0. So I'm going to start at the origin, and I have a slope of 1. That's the line y equals x. Essentially, when we find inverses, we're reflecting that line over, we're reflecting our original line over the line y equals x. Looks a little crazy, right? But if I did that, if I were to fold my graph right like that, this part right here would be that guy right there, the blue part. Do you see that? Green, I'd fold it over, he'd end up down here. This part of my green line would then fold up and flip up here. Have you seen these guys before? They're mirrors. Have you seen those before? So, there's a beveled edge, but I want to show you something. I don't know if it'll show up on the screen, but I have some for you guys here in the room to play with. But it sort of makes a reflection. Do you see? You can kind of see it. See, if you look at the red part right here, you can see a reflection of things that I've drawn, right? So if I line this guy up on my line y equals x, and you look in the reflection here, like I said, it's hard to see, but if I angle it, you may be able to see it. See how it looks a little crazy? I'm not on my line. When I angle it, I lose it. There it is. You can kind of see it, but it lines up. Your reflection lines up. So, if you don't want to touch other people's booties, don't grab it. Okay? You kind of see it? So look, what you're going to look at, you're going to look at the reflection here. It should line up there. So you're going to look on the red piece, and it should line up on your paper. Does that make sense? But when you're done, pass it to another person. Sorry for those of you at home. I'll show you on Monday, okay, if you want to play with it. So what it does is it kind of lines it up. Does that make sense? So you're looking on the red part of it. Did you see it? Yeah. You see it, Wyatt? So sometimes when it's a whole lot of work to do through this, sometimes I think in pre-calc they get the mirrors out and you actually do a whole worksheet with the mirrors, and it does like sideways, and you could do curves and stuff like that. But what those mirrors do is they help us see those inverses. Did you see it, Griffin? Did it work for you, Alex? Yeah. Did it work for you? Kind of cool, huh? Thank you. Let's wipe this down. Anyway, so when we find an inverse, we switch the x and the y, and then we solve for y. Okay? You don't have to graph this pink line here. I just wanted to show you that's what it's actually doing. We're reflecting it over that line y equals x. Think back to geometry. We did those, right? We did reflections and rotations and fun jazz like that. Here's what you were actually doing. You were finding their inverse when you reflect over the line y equals x. Okay, so why is that useful with what we did Monday? Well, two functions, f and g, are inverse functions if and only if both of their compositions are the identity function. And the identity function is the line y equals x. So if I do the composition and I get f of g of x, Fogg and Goff, and I get x for both of them, then they're inverses of each other. Well, my guess is most of you didn't really enjoy doing that composition stuff, right? It was kind of confusing what we were doing. So do you think maybe we could find a better way to determine if they were inverses of each other? Any ideas? Kayla grabbed her calculator. Maybe that might work, Kayla. Sorry, Ray. It might work. We could put both of them in and then see how they lined up. You know, maybe had a mirror or something like that. What about algebraically?
We just do what we just did. And we flip it and then add the top.
Yeah. What if we did what we just did, right? We've got two functions. What if I just look at one of them and say, okay, what's the inverse of u? And if your inverse equals the other guy, then they would be inverses of each other, right? That would be a whole lot easier. Do you like that idea better? Okay, so here's what we're going to do. We're going to find the inverse of 1. It doesn't matter. I usually find the inverse of f just because that's the way my brain works. Okay, so if we find the inverse of f, well, this guy right here is, remember that's fancy y, so I'm going to say x equals 3/4 y minus 6. All right, add 6, so I got x plus 6 equals 3/4 of y. How do you want to undo that? Multiply by 4/3. If you want to do it a step at a time, you certainly can. So I got 4y, but, oh, that's not a y. Where's the next? 4x plus 24 equals 3y. So 4/3 y plus 8 equals, I did it again. Ugh, I'm sorry. Okay, this is the inverse of the f function. Is this the same as that?
Yes.
Yes. So they are inverses of each other. Now, it has to be exactly the same. Signs and everything. Okay? So if it's not the same, then they're not inverses of each other. Okay, do you want to try 4? You try 4. Find the inverse of 1 by switching the x and the y. See if it equals the other one. What do you think?
No.
No, they're not the same, right? My inverse I got, so I switched the x and the y. So I got x equals 3y plus 4. I subtracted 4. Then I divided everybody by 3. You could even leave it right there if you want like that. I don't mind. So they're not the same. So those guys are not inverses of each other. Questions on that? Okay, the last thing on there is it says a one-to-one function. A one-to-one function is a function whose inverse is also a function. You can use the vertical line test. Oh, wait, I lied. You can do the vertical line test to determine if the inverse is the function is one. You have to do the horizontal line test to see. All right. I can't spell right now. Don't talk and write. There. You can do the horizontal line test to determine if the inverse is also a function. So, just a reminder, let's look at our graph, and I will tell you what that means. So, if I look at my graph, and I'm going to look at my original, so I'm looking at the green one here. Remember, the vertical line test means I can draw a line anywhere, and I will only touch my graph once. Remember that? If I do the horizontal line test on it, and no matter where I draw a horizontal line, I touch my graph only once, that means it's a one-to-one function, meaning its inverse will also be a function. Does that make sense? Or the other thing you could do is graph your inverse and see if this guy's a function. Does that make sense? Do the vertical line test on it. So a one-to-one function means it passes both the vertical line test and the horizontal line test. So what is something, think for a second, what would be something that wouldn't pass a horizontal line test? A parabola. Okay? Parabolas are not one-to-one functions. They're a function because they'll pass the horizontal line test. I can't talk. They're a function because they pass the vertical line test. But no matter where I draw a horizontal line, I'll touch it twice besides the vertex. So a parabola is not a one-to-one function. I feel like I just said that completely confusing. Did it make sense? Questions?
Can I go get the truth?
Yes. Okay, so turn the page and let's look at your worksheet. Okay, the top part should go super fast. So you're finding the inverse of each relation, you're just switching the x and the y coordinates. Okay, should be super fast. In the middle of your paper here, it says find the inverse of each function, then graph the function and the inverse. So you're graphing two things. Okay, let's do number 7 together. What do you think? So number 7 says y equals 4. What does y equals 4 look like? A horizontal line, right? And he's horizontal at positive 4. 1, 2, 3, 4. So what would my inverse be? X equals 4, right? Switch the x and the y. Well, there's only a y to switch to an x. So this guy is now a vertical line at 4. Does that make sense? Okay. So you're finding the inverse of all of these guys, and then you're going to graph both of them. So you should see 2 lines on every graph. Sound good? All right. Then down at the bottom, 13 through 18, your answers are yes or no. Now, I should see some sort of work, so don't go look at the answer key and just write yes or no. Okay? So you have to find the inverse of one and see if it equals the other one. Some of them you can look at real quick and say yeah, some of them you can't. Okie dokie, and it has to match exactly. Okay. Questions on any of that?